This is Structure Analyze and Modeling Portal section Time History Analyze, GSA tutorial part. Before you start watching this tutorial, you should have already went through the Time History Analyze individual assignment and have conducted the Time History Analyze hand calculations with the method provided in the Time History Analyze individual assignment hint part. So for this tutorial, you should be able to learn how to conduct a linear time history analysis in GSA. To illustrate the process, similar to what we have done in the time history analysis individual assignment, here assume a model with single degree of freedom system with a natural period of t equal to 1.0 second. The mass is supported by 10 meters high, 500 millimeter by 500 millimeters cross-section size, zero density concrete column, and subject to an excitation of x direction. Given these parameters and the method provided in time history analysis individual assignment, you should be able to calculate the mass value by yourself. So first of all, what we should do is to create a new file and populate the project name. So for the job title, we can say as usual, structural, analyze, and modeling, portal. And for subtitle, we can say time history analyze, and click on next. For the space type, for structural type, you should still space unit is kilonewton dash meter, and you should be aware of the unit of length small. And if you feel confused about the stress unit, you can just change it to megapascal or gigapascal. And we don't need to specify any of other values here, and click on finish, it's fine. Okay, then the next step we should do is to go to the gateway menu, the table tabs, the nodes, and we should input the coordinates for the two nodes, which is 0, 0, 0, 0, and 0, 0, 10. Okay, so let's go to graphic view, and in the one of the directions, open the label node dots, label node dots, and label node numbers. You can see that this is node 1, then that's node 2. And then we can link them together by using the add element scalp tool. Link from node 1 to node 2. And we can have a look at the element number, which is element 1. Okay, then let's go to the element. The element 1 is the bin or the column we just defined. So for the element 2, we need to define a mass element. So we click on this line. We don't do that in here. We use wizard. Give a name as mass. Type, there will be mass. Group is 1. Topology is where this mass is located. So we want it to locate it, see here, at node 2. Okay, so what we need to do is to input again mass, type is mass, so we want it to locate it at node 2, so we input node 2, and the mass property is 1, the property will be defined later. Click finish. Oh. Yeah, there's a problem that you should first click here and use the wizard. Let's do that again. S 2, finish. Okay. So then we go back to graphic view, and you see at node 2 here there is a small square here represent the mass. Okay. So then we should generate the support. We can go to the gateway menu, nodes, restraints, and select all of them. For node 1 there will be all yes, because we want to fix it in all directions. Whereas for node 2, we string everything but not x direction. That's the reason, because the excitation, the ground motion is in the x directions in this model. So we don't restrain x, we want to see how the structure behave in the x direction. So we now open the label restraints and see at node 2 is restraint yz as x, yy z direction, and at node 1 is in cast, so it's fixed in all directions. Then we can close them all, and you go to the define the material property, which is the gateway menu property, materials, and user define. The reason we need to define that because in the standard material we don't have anything zero density, so we select that, use the wizard, input name as concrete, zero density, and material mode should be give the same. Material type is the concrete. We can copy the standard material type, which is in this example that will be the short term. Go to next, and we don't need to change anything except the density because we want zero density material, so we specified it as 0. So notice here that this values is still here the name of the first user defined material. Change it back as material 1, so we should input it again, the name again. 0 density. Okay, so then after we define the material properties, what we do next is to define the cross sections, which is all still at the properties, section properties. And for property 1, we right click, go to the wizard, and define the section property. The name we will populate will be the column. And the material is the concrete 0 density. Structure type, the cross-section type will be rectangular. Go to next. Beware of the unit here, that's millimeters, so we need to define a 500 by 500 millimeter cross-section. And we click on next. Finish. So then we have the section properties for the columns. So we can go to graphic view, turn on the section display, and conduct the visual check. So that's what we want. Okay, so next we need to define the mask property, which is still at gateway menu, properties, mask properties. Select the first line, wizard, and name it as mask property 1 or mask. It's all fine. The mask value that will be 44.3723 turn as calculated in the individual assignment. You should be aware that at the upper right corner it says the unit is turn meter, so here we input 44.373. And we can leave the other things at the default setting. Press OK. And after we define all this, we need to conduct the model property analyze. So we go to the cases and tasks in the gateway menu and click on new analyze task. We can right click and put the new analyze task, or we can just click the new analyze task 2 at the top two bars. Say, for example, the first one there will be model. Model analyze. So we go to dynamic, the model, and click next. And we don't need to change anything here. Okay, and just click next, and analyze now, and it's fine. So let's go back to graphic view and click on the deform image on the right hand side. So you can see that the frequency is very close to 1.0 second. There will be a small difference due to the difference of the calculation method in GSA and hand calculation, but the result indicates that it's very close. So what we have built, what we have constructed is right. Then the next thing we should do is to input the base accelerations, which is let's close this one. Go to the dynamic reactions, dynamic response, load curve. So we need to input a load curve in here. We have been assigned a number for the ground motions. So in these cases, we use NGA number 126 X component. So we select these two, the times and accelerations, and we paste it here. So first we should still copy the time here, the new line. Then we, as indicated in the individual assignment, at the bottom part of the first page, it says, note that the accelerations are reported in terms of g, which is the gravity, and will therefore need to be scaled by 9.8 to be converted to meter per square second. So that's what we should do. We should convert this unit by times 9.8, and that gets what we want. And in addition, we still need to get the absolute maximum absolute displacement, the acceleration here, but that will be done later. So what we should do now is copy the time and the accelerations, and go back to GSA. We click on wizard and paste it in here. Then we can see the log curve 1 diagram, which is the log vectors versus times, and press OK. Okay, after we define the base accelerations, we should define the time history analyzed, which is go to the cases and task, analyze task. We add a new one. That will be time linear, time history, analyze, and select the dynamic response linear time history. Click on next. And model analyze task, that will be task 1, and we use base acceleration because it's a ground motion. The direction is x, and the reason for that is because we assume that the model is subject to the x excitation. For the peak ground accelerations, we should go back to here. Okay. So there's functions for getting the maximum, which is the peak ground accelerations. Yep. Oh, actually, we should do that like. Yep. And then we should check. We also need to put in here. Then we can get the result. Okay, anything went wrong? No, nothing went wrong. Oh, so we can use another ways to import that. Control Shift Enter. Yeah, then we can get the that will be the right formula. But here we get the maximum peak, which is the peak ground acceleration. Copy it. Go to here and paste the value. Okay. The load curve, that will be load curve 1. If you define, different load curves, so you should choose the load curve you need. For damping, we have specified that will be 5% for all modes. Then for the output times, the time interval should go according to here. So the difference between two records, that will be 0.005 seconds. So you put 0.005 seconds here. And stop time in this record, that will be 16.26 seconds. So there will be 16.26 seconds. Go to the next. And before we analyze that, we should go to advanced. See the result, make sure the velocity is clicked. Press OK, finish. And then it start the calculations. And yeah. There's a bit problem with the program, so we need to wait a sec. Okay, so we should now go to the gateway menu, output tab, the nodal result, and go to the displacement. So what we can do is to use change it to the Excel friendly style. But before that, you should be aware that the unit here is millimeter, and what we do is to convert it to meter. You can do that in Excel, but there's a more easier way. You should go to unit, change the unit with the length more to meter, and then change it so we don't need to do that later by ourselves. Okay, so let's press Ctrl Alt and G, change it to the Excel form, and select them all. Copy, and let's paste here. And for the velocities, which is still use Ctrl Alt G and copy them to the. Oh, there's another thing to be aware that actually in the GSA record, the first line is not. It should be set as 0 for the displacement, velocity, and the accelerations. So let's go back for the accelerations. Use same thing. Copy them all. Go here and paste the value here. So then we get our result from the GSA, and we can compare the results we obtained from the hand calculations to see whether the result we obtained here is right. If it's corresponding with these two records are corresponding with each other, so that suggests that what we have done in GSA is correct. So that will be all for the GSA tutorial for the section time history analysis.